Hi, in this video, we'll talk about classes, objects, and events. So, in our previous video, we have seen how semantic nets can be constructed. They are based on the concept of classes and objects. We have understood that how important it is to characterize the entire information that we have into classes. So, for example, person is a class and John is an object, and it can also be called as instance of class person. Such kind of organization would help in representing the world knowledge. The interaction with the world takes place at the level of individual objects. However, the reasoning can take place at the level of classes. So the classes can be represented in first order logic in two ways. The first way is a predicate, like person of John. That means John is a person. This can be one representation. The other representation is class can be represented as an object, like member John person, which says John is a member of person. It can also have this particular notation. Coming to subclass can say that a person is a subclass of mammal with this kind of notation, which can also be represented as person subclass of mammal. So in this literature of classes and subclasses, we usually have the words subclass, subset, and subcategories being interchangeably used. One of the primary reasons that we have classes is to use the property called inheritance. So let's say we have a class food, and we have a property that this class is edible. Now we have a subclass of food. Let's say we have a class fruit. And further, we have another subclass of fruit. Let's say we have apple here. So using the inheritance property, I can say that this property, which is of class food, can be inherited by its child, which is apple. This apple is in fact is an instance of this particular class. So I can say, using the class inheritance property, that apple is edible from this example. This is one of the very important properties that we can get from this particular representation of classes. Individual apples inherit the property edibility from the membership in food class. Subclasses relations organize classes into a taxonomy or taxonomic hierarchy. So if you have observed, we had food, and then we had fruits. We can also have vegetables as a subclass, and then we can have all possible fruits as another subclasses, as well as for vegetables. If you keep on doing such kind of a class and subclass relation, what you end up is a taxonomy. The most common use of taxonomy is seen in animal kingdom classification, where all the species are classified in such a structure of class and subclasses. So what is the relation between logic and classes? The logic makes it easy to state facts about classes, either by relating objects to classes or by quantifying over their members. So let us take a few examples. Let us say I have an object BB9, and I want to say that this is a member of a class basketballs. This can be represented in logic as follows, where BB9 belongs to the member class basketballs. Let's say I want to say that basketballs is a subclass of balls. That can be represented like this. And also, I can have properties for a class. I can say that all members of a class has some property. That means I want to say that all members of basketball, if X is a member of basketball, that implies X has some property that can be like, it can be spherical, it can be orange, any other property. the vice versa can also be done. The members of a class can be all recognized by some properties. I can define classes using properties. So let's say I take an object X and I say that object X has property that it is orange in color, it is round in shape, it is having a diameter of, let's say, 9.5 inches, and it belongs to the class balls. If I define properties for an object, this can also be contributing as defining a class basketballs. This would imply that X is a member of basketballs. A class as a whole has some properties. This can also be represented in first order logic, where a class, dogs, would have the property that they are all domesticated species. Then we can look at the relation between classes. We have seen that classes can have subclasses as well, but we can also have relation between two classes which are not subclasses of each other. One kind of relation is a disjoint relation that says two or more classes are disjoint if they have no common members. Like in the case of male and female, these are two classes where we don't see any common member, and these are both subclasses of animals class. And then the other kind of relation between classes is an exhaustive decomposition that says that if a class has, let's say, subclasses, and it is called as exhaustive when all these subclasses become the complete set that constitute that class. So for example, for the class months, if we have a list of subclasses as all the months, like Jan, Feb, March till December, if we list all the months, they become exhaustive. They are the complete set of subclasses for this parent class months. And partition is a relation between classes when they have disjoint as well as exhaustive decomposition among them. So in the same example, list of all months is a partition for the class months because they are exhaustive. At the same time, they don't have any common dates among them. They are disjoint as well. So one other example that we can have of these relations is that the classes animals and vegetables can be called as disjoint classes because we don't see any common members among them. And the exhaustive decomposition for all the citizens of North America, they can either be from Americans, they can either be Americans, or they can either be Canadians, or they can be Mexicans. So this is an exhaustive decomposition. So all North Americans can be categorized into any one of these three nationalities. However, we cannot call them as a partition because some people might have dual citizenship of American citizen as well as Canadian citizenship. So for partition example, we can have the months as a good partition example. So as I said earlier, we can also use certain conditions over an object in defining classes. So I want to define a class saying that if X is an object which has such and such properties, like it being orange in color, round in shape, with such a diameter, and also it belongs to certain class, I can use these properties in defining a class basketballs. For another example, if I want to define a class bachelors, I can have properties like the object should be unmarried and should be belonging to the class adults and should also be belonging to the class males. Only when all of them are in conjunction, only then I call it as bachelors, and the vice versa relation holds there. So in each object, it can be a part of another object. For example, one's nose can be a part of one's head, just like Hyderabad is part of India. So we have certain objects being part of another object. Such kind of relation can be attributed or can be defined using part of predicate. So we can use this relation to define that argument 1 is part of argument 2. Part of Bucharest and Romania says that Bucharest is in Romania, as well as part of Romania Eastern Europe says that Romania is part of Eastern Europe. In most of the objects that we have seen, objects would also have properties like height, mass, cost, as you have seen in the basketball case. And we would like to assign a value to these properties. We want to say the height of a object of a person class would have such and such values, and we call such values being assigned as measures. Whenever you assign some values, we call that as measures. Such properties are represented with the units function. So if you want to represent height of an individual, we represent with the units function, and which has an argument as a value that we assign for that object. So let's say we have a line segment here, and I want to measure this line segment in terms of inches. So what I would do is, let's say I call this line segment L1, which is a variable. I can represent length of L1 in inches. Inches is my function, and that the argument will be the value of this particular measure. This can also be represented in centimeters. Centimeters as a function, this is a unit function, and I can have the value as an argument here. We can also have conversions between units. So inches can be converted into centimeters by a factor 2.54. So measures can be used to describe objects as well. So if you want to say that the basketball object would have a diameter measured in inches and the value will be 9.5 inches, you can use this measures notation to define properties of the objects. Similarly, the list price of basketball can be defined in measures with a dollar function. Well, most measures can have values, but there are other measures that also do not follow an agreed scale of values. If I have examples like some of the exercises from a textbook are difficult, or these kind of desserts are more delicious, so such and such measures don't have any agreed sense of value. Some people might have a different agreement on scale of 1 to 10, and some other would have a different value that will be associated for this word deliciousness. So what do we do in such scenarios? So instead of assigning a value for representing that degree of variance, we will rather order these measures. So if I want to represent that, if anyone have worked on physics in the +2, they would know that the examples from the Erudito textbook are quite harder than examples from textbook written by H.C. Verma. So if you want to represent this particular sentence that exercises in IE Erudito are tougher than H.C. Verma, I can use the following notation. Instead of giving a value for the exercises, now I will order these values. So let's say E1 is a variable that belongs to the class of exercises, as well as E2 is another variable that belongs to the class of exercises, and E1 is written by Erudito, whereas E2 is written by Verma. That implies that the difficulty of E1 exercises is greater than the difficulty of E2. With this particular greater than symbol, we have now ordered these measures without actually assigning any values. When we talk about objects as well, there is a significant portion of reality that cannot be labeled as objects. Let us have that, we can name it as stuff for now. Let us look at an example. What do I mean by that? If we consider two objects, banana and butter. Whenever you look at a banana, you can count the banana, or you can weigh the banana, or you can tell that this is the number of bananas that you have. But when it comes to butter, there is no obvious number that you can associate it with. There's no object called butter. Even if you have the butter and cut it into multiple pieces, each single piece can still be called as butter. So these are not necessarily objectified as proper objects in our ontology notation. And let us for now call them as mass nouns, where they primarily are categorized by the mass intrinsic values, and the remaining objects can be classified as count nouns, where we can individually count each item of those objects. Like butter and water cannot be counted, so we call them as mass nouns here. However, we need to represent such kind of stuff as well in our ontology. So we know that even after creating many small pieces of that stuff, we would still call that each piece as the same class. So if we cut the butter into small pieces, we know that each piece would be referred as butter again. So let us define a class butter that we can represent in our ontology. Let's say butter represented as the same name. And now we want to say the property that each small piece that I divide this into, P1, P2, and P3, all of them still is part of the class butter. I can represent that information in first order logic. Let's say I have an object B that is belonging to the class butter, and then I can use the part of relation that I defined earlier, part of P. Let's say P1. I made this small piece as P1. P1 is part of B now. Whenever I have such kind of a part, that would imply that P1 would also belong to the class butter. This definition would say that we are talking about the mass nouns instead of the count nouns. We can also add attributes for such classes. Like if you want to say that the butter has an attribute of melting point at 30 degrees Celsius, then we can say if B is an object that belongs to class butter, that implies that the melting point of B is 30 centigrade. So what exactly is happening? What is the difference between such kind of substances compared to the one that we are seeing earlier is that there are two kind of properties that are different among these two variants. The intrinsic properties are something that retains with every division of the substance. Like in the case of butter, whenever we further cut into pieces, the intrinsic properties like the density, the flavor would retain. And those are the intrinsic properties that would characterize them. The extrinsic properties are something that are not retained with a division, like weight or length, etc. And so far in all our search strategies or in our state representations, we have seen that any action that we take, let's say we want to find a path from route city A to city B, then we take multiple paths in between, and all these actions that we are taking in between are considered as one instantaneous actions, like the one discrete actions. If you want to move from city A to city C, then it is just done in one particular action. However, in real life, this is a continuous process. We need to drive from city A to city C and then further down the line maybe to D and then E and then to B. This is a continuous process which was not handled in our previous representation of actions. So to handle such scenarios, we define something called as an event calculus. This would help us in defining events, like while you're driving from A to B, you have done certain tasks like maybe listening to podcast or maybe handling some certain other task. You can define such aspects using event calculus now. It is based on points of time rather than on situations. So what event calculus does is that it defines two things. One is the fluents, the other is the events. A fluent is nothing but an object. An example of a fluent is that we have a predicate at which says Shankar is at bits. And this doesn't say that it is a true or false. A fluent just says that it is an object that refers to the fact that Shankar being in bits. We don't know whether this is true or false. If you want to calculate whether this fluent is true, then we use a predicate T. Predicate T is used to calculate the truth value at a time dependent factor. Earlier we used to calculate truth values without having time in the picture. Now we have time as a factor in calculating the truth value. So this particular statement holds at particular time intervals but not all the time. So that we are now able to define using event calculus. Whereas events are described as instance of event classes. So let us take an event E1 which says Shankar is flying from San Francisco to Washington DC. This can be described as event E1 is a member of class flyings, and event E1 has the flyer named Shankar. The origin of such event is San Francisco, and the destination of that event is Washington DC. So now we have described an event which has a flyer and which has a class flyings, which has the origin and destination in our logic statement here. Then we move on to some of the specific predicates that we have in the events. One such is happens. Happens is a predicate that is defined in the event calculus, which says that event E1 took place over a time interval I. The time interval is usually defined by two values, t1 and t2, where t1 is the start time and t2 is the end time. So just to give an idea of what kind of predicates we might have in the event calculus, this is one version that is listed here. So these are all the predicates that are only defined in the event calculus. We'll start with t. T is a predicate which says whether this fluent, whether this fact holds true at this particular time t. And the second predicate happens says that whether the event E, which we have defined using logic earlier, happens over the time interval I. And then there's this other predicate which says initiates. That means that the event E would cause the fluent to start hold true at time t. So because the event has happened, that would influence the fluent, which is a fact, to start being true at time t. And the opposite of initiates is terminates, where it says that event E causes the fluent to stop being true at time t. Clipped is another predicate which says that fluent F ceases to be true at some point during time interval. We are not sure exactly the timestamp where it stops being true, but we know at a time interval I, which is from t1 to t2, somewhere here the fluent F has stopped to be being true. And restored is the opposite of clipped, which says the fluent F becomes true sometime during the time interval. So events also has a little ambiguity. So what we have described so far in the events have a discrete structure. They have a definite structure, like Shankar's trip would have a beginning, would have a middle, and would have a end. What if you have interrupted this particular discrete event structure? It would be something else altogether. So let us take the example of Shankar's flight. Shankar's flight, let's say, holds for 2 hours, and in between 2 hours, Shankar's flight has to take a D route and has to stop at another airport. And then during that process, Shankar has taken up certain tasks. We couldn't explain such kind of processes with the event that we have defined earlier. For such a scenario, we have defined what we call as a processes. These are nothing but the classes of events with such property of subintervals, and these are called as process classes or liquid event classes. So any process E that happens over an interval also happens over a subinterval. So we have this predicate from the event calculus which says that E variable is a member of class processes, and E happened during this time interval t1 to t4, which would also mean that it can happen between a sub-time interval t2 and t3. Let's say we have a time interval t1 to t4, and I say there is a process E that lies in between t1 and t2. That would suggest that there is a time interval t3 and t4. The process would have happened. This would allow us to define events that would happen in between an event. You can think of this as analogous to how we were discussing about objects and the stuff, the count nouns and the mass nouns. That is an analogy that can be used here, where this kind of events are called as liquid events because they can be flexible with the time intervals they have, and these kind of events are called as non-liquid events. And the event calculus also allows us to talk about the time and the time intervals. There are two kind of time intervals: the moments and extended intervals. Moments is just defined as a time interval with zero duration. So if I is a moment, then it suggests that duration of I is 0 seconds. So the time intervals has the partition set of moments and extended intervals. So we are now defining the time intervals more concretely, and that has two subclasses, which is a partition of the intervals, and they are moments and extended intervals. The scale of a time interval is something that all these moments lie upon. So whenever you want to define any time interval, you need to first come up with a time scale. What do I mean by that is that you just need to take a reference point. For this illustration purpose, we just took 1900 Jan 1st 00 am as our starting point, and any moment that is described on this time scale is defined as how many seconds have been elapsed since that beginning of time. So that is a time scale that we have to come up with before we start discussing about time intervals. And the begin and end is the earliest and the latest moments in the interval. Whenever you have an interval and you say the begin of this interval is the starting point, the end of this interval is the latest moment. The function time delivers point on the time scale for a moment, and the duration would give the difference between end and the start time. Let us look some of the terminologies of defining a time intervals. Interval I is nothing but the duration I, which can be defined as the difference between the end of the interval minus the beginning of the interval, where we have this function of time on top of the end interval. Time would only give us the number of seconds that have elapsed since the beginning of the time. As I said earlier, our reference point is 1900 Jan 1st. So the time here says that the number of seconds elapsed since the beginning is 0. Similarly, if you do it for 2001, the number of seconds is mentioned here. Similarly, if you do the end of AD 2001, which is December 31st, you will see a difference 0. So the duration clearly of AD 2001 can be a difference of these two, which will be the value shown here. A function date takes time arguments like hours, minutes, and etc. and returns a time point. It is just an extension of the function time, and it takes exact details of what is the number of hours, what is the number of seconds, minutes, and the entire date, and then returns the number of seconds that have elapsed since the beginning of the time. Now that we have defined the time intervals and the functions that would be used on top of the time intervals, now we can define a relation between events. So two intervals meet if the end time of the first equals start time of the second. Let's say we have two time intervals I and j. Now we are defining relation meet. Meet would say that the end of I is when the interval j has started. That means, let's say I has an interval t1 to t2 and j has an interval t2 to t3. So as in when the I has finished, the j has immediately started. That means these two intervals follow the relation meet. I meets j. Whereas before says that j has begun before I has ended. So if I has t1 to t2, then j might have started before I has ended and finished later on. So this particular scenario where j has started before I has ended is characterized as before. After is just the same notation as before, only the arguments are reversed. During says that while we are having the j interval, the I has happened during the j interval. So I happened during j is represented as during. So j is represented like this and I is represented like this. So I has started and finished within the interval of j. That is represented as the function during. Whereas overlap says that I and j actually have the relation as follows, where I has an interval of t1 to t2, and j says that this overlap relation guarantees that the end time of j is after the end time of I. In our previous relation, where we are looking at before and after, we were only concerned with the start times and end times, but we don't know whether the j has ended before the I has ended. Whereas in overlap, we are guaranteed that j has begun before I has ended, and it has finished after I finishes. And the begins of ij says that they both begin at the same time. Finishes says that they both end at the same time. And equal is nothing but the two intervals are exactly equal. This is a pictorial representation of all the relations that we have seen so far. Meet is when they both meet, and start is when they both start at the same time, as we can see here. Before and after, that means I happened before j, and after j of I says that j has happened before I. Finishes says that they both end at the same time. Equal is obvious that they both have the same time intervals. And overlap here says that the j starts before I ends and finishes after I finishes the interval. And during says that j has a bigger time interval and I happen during that time interval. So using these time intervals, we can now describe events like the reign of Elizabeth II immediately followed that of George VI. If we want to represent such kind of knowledge, we can now use these time intervals. So, and also we have the information that the reign of Elvis overlapped with the 1950s. 1950s is usually the period from 1950 to 1959. So, Elvis period was in overlap with 1950s. So now we can represent that using our predicates we just seen. That means for the first case where the reign of Elizabeth II immediately followed that of George VI, that says that the reign of George VI and the reign of Elizabeth II follow the relation meets. And the second relation has an overlap relation of 50s and the reign of Elvis. And we can describe the 50s as it began in 1950 and it has ended with 1959. So far we have seen agents that are constructed with beliefs, as in with uncertainty. However, we haven't yet understood what knowledge do we have about these beliefs. So having knowledge about one's own knowledge and reasoning process is useful for controlling inferences. It's like a meta knowledge that would tell us what kind of knowledge do we have, how confident are we about the knowledge that we have. For example, let's say Alice asks Bob, what is the square root of 1764? And Bob says, I don't know. And if Alice insists that think harder, then Bob should realize that with some more thought, this particular question can be answered. So there are questions which would need some kind of reasoning process, that how much of information you know and how you can get that answer if you don't know what information you have. And another example can be Alice asks Bob, is your mother sitting down right now? In such a case, if Bob says, I don't know, then there is no point of thinking harder. The Bob should realize that thinking harder doesn't really help. Rather, what he should do is just ask his mother whether she is sitting down or not, and that would give us the truth statement of that particular question. So, this information says that whenever we are posed with queries, and based on whatever information that we have, we should know how to proceed forward with the reasoning process, whether we should say that we really don't know, or whether we should keep asking more questions so that we get the right answer. So we need a model of our mental objects, that is nothing but a knowledge base. A knowledge base is a model of the information that we have in the world. Now we are taking one step back and saying that we need a model of model. And we also need a model of the mental process that manipulate these objects. So how we can define such a model? To start with, let us look at some of the attitudes that we can associate with such a model. They can be beliefs, they can be knows, they can be wants, they can be intents, and they can be informs. These are some kind of knowledge you have about the knowledge base. Maybe you really know certain statements are true. Maybe you are not sure, but maybe you want to know. You want to know certain kind of information, and maybe you think they are true, and then you call it as a belief. So all these attitudes informs your knowledge about the knowledge base. So they do not behave like a normal predicate. For example, Lois knows that Superman can fly. This can be represented using the propositional attitudes like knows, Lois, and Superman can fly. But if it is true that Superman is Clark Kent, this is, let's say Superman is Clark Kent is true and is known to everyone, then we must conclude that Lois knows that Clark can fly, because Lois knows that Superman can fly, and then we have information that Superman is Clark Kent. So we should say that Lois knows that Clark can fly. So this particular deduction or reasoning is a consequence of equality that we have in logic as well. To handle such kind of reasoning of knowledge about knowledge, we built something called as a model logic. The regular logic is concerned with single modality, where we have a proposition and we assign a truth value, whereas model logic include model operators. We have something defined as model operators that take sentences as arguments. For example, there is an agent A who knows that P is represented, who knows about P, like in Superman can fly. That can be represented in our model logic as follows: K, A, P. A is an agent and P is a proposition, and K is our model operator for our attitude knows. It takes two arguments, the agent and the sentence. The syntax is pretty similar as first order logic, but the semantics are pretty different from the logic. Thank you, and in our next session, we'll talk about forward and backward chaining.